Welcome back, everyone. We are in section 11.3, looking at using our chi-square distribution for another type of hypothesis test. In this section, it's going to be a test for independence. So the chi-square test for independence is used to determine whether there is an association between a row variable and a column variable in a contingency table constructed from sample data. So the main key here is that the null hypothesis is that the variables are not associated. We just assume that the variables are independent, okay, that they have nothing to do with each other. The alternative hypothesis is that the variables are associated, or that they are dependent upon each other. So another nice thing about setting up this hypothesis test is that, again, the null hypothesis and alternative hypothesis will always be the same. The null is always that they are independent, that they have nothing to do with each other, and the alternative is that they are not independent, okay? That they actually do have a relationship of some sort. So if we look at what we're going to need for this one, in the last section we had expected counts. Here we're going to have expected frequencies. So it's the same kind of idea based on probabilities from past experiments, from data that we use. We can look and say how much would we expect to have for each of these categories. And then we're going to use those expected frequencies to then help us draw our conclusions. So in order to find expected frequency, we're going to take the row total times column total divided by table total. Okay, so there will be a row and a column for each of these terms. We multiply the row total by the column total, divide by the entire total in the table, and then that'll give us our expected frequency. So let's go ahead and look at an example of this. So in a poll, 883 males and 893 females were asked if you could have only one of the following, which would you pick? Money, health, or love? Their responses are presented in the table below. So men, 82 of them said money, 446 said health, 355 said love. So that's for a total of 883. And then women, 46 said love, or money, 574 said health, and 273 said love, for a total of 893. Okay, and then you add up all of those people, and that leaves us with 1,776 total participants. So in order to get the expected counts for each of these, so we're going to be looking at each of these items in the table. So this is the expected frequency of men who said money. Then we'll look at the expected frequency of men who said health, then men who said love. So we'll do this one, this one, this one, and then women and money, women and health, women and love. And then by the time we're done, we will have an entire contingency table full of these expected frequencies. So I'm just going to do the first one, maybe two, because I think you'll kind of catch on to it. It's pretty formulaic. But for the first one, so for the expected frequency for men and money, so it's the row total times column total over table total. So if we're in this cell right here, the row is this. So the row total is 883. The column is this one. Column total is 128. And then the table total is just the total number of participants, so that's 1,776. So the expected count for this first one is going to be approximately 63.64. Okay, so based on this data that we have from this poll, we would expect 63.64 in this category moving forward. So we have 63.64. And then we would do the same calculation, so like for the men health section, we would do row total times column total, so 883 times 1020 divided by table total, which is 1776, and that would be 507.13. And then if we just fill in the rest of these, it's the exact same calculation. For men and love, we get 176.50. For women and money, we get 23.13. Women and health, we get 512.87. Women and love, we get 315.77. So this is now our contingency table for the expected frequencies. And we're going to be able to use this to find our test statistic and run a hypothesis test, just like we did in the previous sections. So if we look now to the next page, our test for independence, again, the null hypothesis is that they are independent. The alternative hypothesis is that they are dependent. We'll figure out what we want for alpha. And then the test statistic is computed exactly the same way as it was for the goodness of fit test. The only difference is that instead of an expected count, it's technically an expected frequency, but in essence they are the same thing. And then we're going to, again, use Desmos, use our technology to find the p-value, and then use that to draw our conclusion for this hypothesis test. And the one thing that it doesn't mention in here that I do want to take note of is the degrees of freedom for this test for independence. So our degrees of freedom is going to be the number of rows minus 1 times number of columns minus 1. So number of rows minus 1 times number of columns minus 1. That'll give us our degrees of freedom. And then we draw our conclusions appropriately. Here's the calculator steps for doing this. Now let's go ahead and finish through this example. So we have our poll of 883 males, 893 females, and they're asked which would they pick, money, health, or love. We have their responses here. We have our table of expected frequencies here. And we want to test the claim that gender and response are independent at the 0.05 level of significance. So again, we always start off establishing our hypotheses. The null is that they are independent, and the alternative is that they are dependent, or that they are related in some way, right? Their gender and then how they responded to this survey. We can make a note for the degrees of freedom just off to the side over here. There are 2 rows and 3 columns. So our degrees of freedom would be 2 minus 1 times 3 minus 1. So that's 1 times 2, which is just 2. So we have 2 degrees of freedom. When it comes to computing the test statistic, we take observed minus expected squared over expected, the same way we did in the previous section. And we're going to go component by component here. So we would have 82 minus 63.6 squared over 63.6 plus the next one, plus the next one, plus the next one, etc., all the way until we get to the last one. So there are going to be 6 terms here. So the last one, 273 minus 315.8 squared all over 315.8. And this value, if you run this computation just in the calculator or in Desmos, this number is actually very large. We get 228.88 approximately. Now, if you think back to what we've done with the normal curve, with any of these distributions, most of the data lies within, say, 3 standard deviations of the mean in a normal curve. Chi-square is not that different. It all lies pretty closely together, and that would be if we had a value around like 3 or 4 or 5. We're at 228, almost 229. This value is huge, and it's going to be way off the charts, but let's look at it. So our degrees of freedom are going to be 2. So you can see even just with my set at 10 there, it's already getting pretty high. When I say pretty high, I should say the area is getting very small, right? That p-value would get very tiny very quickly, and that's only at 10. If we set this value to 228.88, you can see that the p-value is so incredibly small that Desmos basically considers it to be 0. And you can see we can go back a long way before we get back, there we go. So even like 26, 27, 28, 29, by the time we hit 30, the number is so small that Desmos doesn't even recognize it because it's incredibly tiny. So as far as we're concerned, this is essentially 0. It's just that infinitely close to 0. So our p-value is going to be 0, which is certainly less than the alpha value of 0.05. So because the alpha value is less than, or excuse me, since the p-value is less than alpha, we can reject the null hypothesis and then render our conclusion. So we can say that there is sufficient evidence, I would say there is very significant evidence, to conclude that gender and response are dependent. So this test is saying that there does appear to be some relationship between those two variables. And then we can't make any confirmations about this because this is just based off of one survey, one sample, but that gives us the conclusion to this problem. So that brings us to the end of section 11.3. Next time we will look in section 11.4 at one final test utilizing the chi-square distribution.